Hi, my name is Kalle Rutanen. This is O-Notation in Algorithm Analysis, Part 2, Local Linear Dominance. Recall from Part 1 the definition of linear dominance. Linear dominance is a relation on the coast functions defined by f is dominated by g if there exists a positive real number c such that f is at most c times g at every point. Linear dominance formalizes the dominance relation, which was given by abstract properties. Local linear dominance is a generalization of linear dominance, which means that linear dominance holds on a large subset, not everywhere. It formalizes the term asymptotic analysis. Local linear dominance is interesting because it can sometimes be used to deduce linear dominance more easily than by the direct definition of linear dominance itself. To understand local linear dominance, we need to understand the term large subset. A filter basis on an input set X formalizes the concept of a large subset of X. A filter basis F on a set X is a set of subsets of X such that if A and B are in F, then there exists C in F, which is contained in the intersection of A and B. Example, if we look at the real number line and look at the set of right half spaces where the half face starts at an integer, then that collection is a filter basis. On the real plane, upper right quadrants form a filter basis. And also, the complements of bottom left quadrants form a filter basis. And here's a filter basis which consists of the neighborhoods of 0. This filter basis consists of the neighborhoods of integers. If we take the intervals from an integer n to n plus 1 with the endpoint excluded, then this is not a filter basis. The complements of the above sets are not a filter base either. There is a filter basis for every input set X. Suppose S is a subset of X. We connect the filter basis on X with those on X by requiring induced substructure, which means that the filter basis on S is obtained from the filter basis on X by taking the intersections with S. Local linear dominance means that linear dominance holds on a large subset. And formally it means that we can find a set in the filter basis so that for each point in that set, F is linearly dominated by G. Example, linear dominance is local linear dominance where the filter set consists only of the set itself. Traditionally, in algorithm books, the dominance relation has been defined as local linear dominance with a filter set given by the right half spaces on the non-negative integers. Here's an example which shows that 17n plus 20 is dominated by n squared plus 3n plus 1 in the sense of the traditional local linear dominance. We would like to connect local linear dominance with linear dominance. A set S is cofinite in a set X if S is a subset of X and the complement of S in X is finite. Here's a connection to linear dominance. When the cos function g is positive and the sets in the filter basis are cofinite, then linear dominance and local linear dominance are equivalent. This allows to use local linear dominance as a tool for deducing linear dominance. And here's an example. Suppose we have these traditional filter bases. We already showed that 17n plus 20 is locally linearly dominated by n squared plus 3n plus 1. Since the set in Fn are cofinite in n, and n squared plus 3n plus 1 is positive, we also have that 17n plus 20 is linearly dominated by n squared plus 3n plus 1. What makes local linear dominance even more useful is that it can be characterized by limits. The limit superior of a cos function f along a filter basis f in X is defined by this expression. For every set in the filter basis, we will look at the supremum of the function f in that set, and then we take the infimum over all the filter basis sets. Example, suppose the filter set is a traditional. Then we want to look at the limit superior of this term. It's given by 5, and it's intuitively, you can see it from this picture. The function itself does not converge to 5, but the reoccurring peaks will. F is locally linearly dominated by G if and only if the limit superior of f divided by G is finite, where the limit superior is along a filter basis on a set where the f is positive. And if there's a division by 0, then we will assume that that's infinite. For the limit superior example we had before, we had that this limit superior is 5. Since 5 is a finite number, we can deduce local linear dominance. As a special case, f is linearly dominated by G if and only if the supremum of f divided by G is finite. So the following examples of blow up and zeros demonstrate why a local linear dominance other than linear dominance cannot be used as a dominance relation in algorithm analysis. Here's a problem to compute this function. A Python algorithm to solve this problem is here. If we compute the cos function for the number of subtractions performed by this algorithm, we get that it's maximum of -n and 0. And its graph looks like this. So suppose the filter sets in Z are given by these traditional filter sets with the right half spaces. Then we get that the cos function of A is locally linearly dominated by 0. So according to this local linear dominance, Fe essentially uses 0 resources. So calling the algorithm on negative numbers allows to consume resources without being noticed by local linear dominance. The following example shows that the blow-up can also happen in a bounded set. So here is another problem, which is a function from real numbers to non-negative integers. And here's a Python program to solve this problem. The coast function for this algorithm is here. And the graph of that coast function looks like this. There are infinitely many blow-ups, and each blow-up is contained in a bounded set. Suppose the local linear dominance is not linear dominance. Then there exists a point which some filter basis set misses. And suppose we are only interested in the number of performed additions when analyzing coast functions. Then the following algorithm has a coast function which is the constant 1. And it's equivalent to 1 under the local linear dominance. And here's another algorithm that has a coast function which is otherwise 1, but at the point P it's 0. According to the local linear dominance, this is also equivalent to 1. Consider the following algorithm G, which takes in n, an integer, and repeatedly calls f at point P. Suppose we know that algorithm f has a coast function which is equivalent to 1 under the local linear dominance. What can we say about the coast function of g? Either g is equivalent to n or g is equivalent to 0. That is, the equivalence class of f does not contain enough information for us to be able to infer the equivalence class of g. This shows why local linear dominance, apart from linear dominance, is not suitable for a dominance relation in algorithm analysis.